So welcome back. I hope you had an enjoyable weekend. And if you noticed, I was busy yesterday putting documents up on Blackboard. So if you haven't had a chance to check the Blackboard, a couple things you want to watch out for. Quiz 1 is posted. Make sure you look at that. You look at the due date, and you're going to turn that in by uploading it to Blackboard. There's a link for you to click on. So that's there. Obviously, the week 2 stuff, all the documents for week 2 are present. And there's another assignment called How Big is the Universe? That is if you remember on the first day, I mentioned to you that I'll give you these outside assignments that count as a quiz grade. They're meant for you to learn from, but also to kind of give you, kind of help your improve your quiz score. So if you do the assignment, you give it your best shot, you're pretty much guaranteed to get 100 on it. So do a good job on it, and then that'll count as a quiz grade. I forget the due date, but you want to look at that. That's another one that you will you'll upload that to Blackboard. As far as lab tomorrow, on Tuesdays we meet for lab face-to-face. Lecture is 3 days a week, and we do that online. Tomorrow, we will not meet for lab face-to-face. The first lab, you were going to go out, you're going to get your meter. You still have time to do that, your digital multimeter. There's a video you're going to watch. You'll watch the video with your meter right there. You'll go through, you'll learn about how to use the meter, and you'll learn about voltage, current, and resistance. And then you'll write some stuff up for me and submit it to me. So that's lab 1. Lab 2 for tomorrow, I have an assignment for you to do. I'm going to plan on meeting, not tomorrow, but a week from tomorrow. But again, what I'm doing is I'm watching the numbers, the COVID numbers. I think last time I checked, we were still in the purple. I'm going to wait till the numbers drop down a little bit, and then I'll feel a little bit safer with you guys meeting. Obviously, we're safe where we are, but we got at some point meet face to face. So tomorrow we won't meet face to face, but I will have an assignment posted for you to do, and we'll plan on meeting a week from tomorrow. However, I'm going to watch the numbers. If they're still really high, I think right now they're dropping, but I don't know where they are exactly. So I'll keep my eye out, and I'll let you know if we're going to meet face to face. But that's the plan. Before we get started, does anyone have any questions for me?
I have a question.
Sure.
So for that multimeter assignment, you asked us to upload a picture of our multimeter. Do you mind if we put our one-page summary and the picture of the multimeter on the same document?
Yeah, that's what I want you to do. I want you to embed the picture in your document, make it like a report with a picture on it. So just submit one file with the photograph or copy of your meter in your report. That's what I want.
Thank you.
Anybody else? All right. Well, let's go ahead and get started. And if you think of something you want to ask, you can ask me at the end of the class. Well, today's lecture is actually pretty important. We still haven't talked about any electrical stuff. Last week we dealt with what I call engineering fundamentals. We dealt with the fact that mathematics is the way scientists and engineers express concepts and ideas. We looked at and talked about systems of units. We looked at this idea of a quantity, that if I want to express a physical quantity, I got to have two pieces of information. I got to have a number, and I got to have a unit. And so we spent time talking about how to represent that number. If I have a really, really big number or a really, really tiny number, well, it's kind of common in science and engineering to use either scientific notation or engineering notation to put those numbers in a more compact form. So we talked about how to express the number part of the quantity. If we have a number in engineering notation, we can use that table of metric prefixes to make a substitution for the power of 10, and it gives us a different way of talking about the quantities that we'll deal with in this class. So we looked at that. And then we finished by talking about measured numbers. We gave a definition for error. We gave a definition for a significant figure, a significant digit. We talked about precision, and we talked about accuracy. But we still haven't done anything electrical. And to be honest with you, even this week, we won't get to the electrical stuff. Well, I shouldn't say that. We'll get to the electrical stuff. But this is kind of the foundation of all the stuff we're going to going to deal with for the rest of the semester. Today, what I want to do is I want to talk about the nature of voltage, the nature of current, and the nature of resistance. You'll be surprised how many technical people, even engineers, they deal with voltage or current or resistance, but they have no idea what some of those terms mean. So I mentioned on the first, I believe I mentioned to you on the first week or first day of class that when I teach this course, I teach from first principles. And what I mean by that is it's based on physics. And so we're going to learn the physics of voltage. How do I create a voltage and what is it? The physics of current. What is a current? And then resistance. What is resistance? So you'll know from a fundamental point of view exactly what you're talking about when you use those terms. Now, often when people teach a course like this, they don't even go into that kind of detail. But I find that understanding what you're really dealing with, the nature of voltage and current and resistance, if you understand that, it makes topics later on in the course, it makes topics in other courses a lot easier to understand. So I choose to spend time going through and figuring out and discussing exactly what these quantities are that we'll be dealing with for the rest of the semester. So I'm sure everyone in the class has heard of voltage. I don't know if you know what it is, but you've heard of it. You probably know that if I want voltage, I got to plug something into a wall or I got to hook up a battery. Most people have heard of voltage. Probably pretty much the same way current. People understand what current is, or at least they've heard of current. You might know that if you blow a fuse or your breaker trips in your basement, you can replace the fuse with a fuse of a certain number of amperes. That ampere is a unit for current. So most people, or a lot of people understand the idea of a flow of something. And then resistance, the word kind of says what it is. It's an opposition of something. But what I want to do is dig down deep into these terms, these physical quantities. These are the big three. These are the ones we'll deal with for the whole semester. Matter of fact, if you have an electrical major, this will be what you deal with. These three quantities, what you deal with for the rest of your working experience. So it's important. So I want to start by reviewing something that hopefully you looked at in maybe high school or somewhere along the line, because to get to understand these three quantities, there's some other things we got to understand first. So I want to go to some of the other things we got to get out of the way so that we can answer these questions. What is voltage? What is current? What is resistance? So what I want to do first is I want to review a topic that, as I said, I hope maybe you guys looked at in high school or junior high school. I want to talk about the atom. We'll discuss the atom. Now, I highly recommend, I don't have any problems here on the bottom of the topic sheet. However, I do have another sheet that has some practice problems on it posted to Blackboard. So I don't think we'll get that far today where we actually do a calculation. We'll do that next class. We'll do that on Wednesday. However, I would recommend having the topic sheet out just so you can follow along and just kind of know what the topics are we're dealing with, and maybe you can jot some things down on the topic sheet if you need to. So remember, the goal is to answer the question, what is voltage? What is current? What is resistance? So by Friday, by the end of this week, you should be able to answer in detail you should be able to describe what voltage is. How do you make a voltage? You should be able to tell me what exactly is current. And you should be able to talk about resistance. On Friday, I expect everybody to be able to do that. And we'll see how it goes. So let's start by talking about the atom. What is an atom? Well, the Greeks, the people before Aristotle, philosopher Aristotle, the Greeks kind of figured out that everything in the universe is composed of these small little indivisible things called atoms. Now, it's pretty amazing if you think about it, because we're talking about before Christ, BC, before Christ. And these people actually, through deductive reasoning and logic, deduced that there must be some smallest piece of a particle where if you go below, or if you could go smaller than that, then you couldn't recognize the particle for what it is. And they call that particle atom. We pronounce it atom. And the Greek translation of that, atom means indivisible. You can't cut it. And so the Greeks correctly reasoned that there must be these tiny little particles called atoms. So they were right, but they were wrong because they thought about, or at least they thought of atoms as being the smallest particle you can have. Well, now we know that even the atom itself is made of smaller particles called subatomic particles. Atoms are composed of electrons, protons, and neutrons. And now we understand that even those subatomic particles are even composed of smaller particles. And every time we peel the onion back, we see that there's something else there. So they're wrong in that they thought that atoms were the smallest thing that you can have. You couldn't go below the level of an atom. But they were right, and amazingly right. The fact that without any computers, without any of the powerful equipment that we have nowadays, they were able to use just their brain and logic to deduce the fact that there must be something called an atom. And so they thought about atoms as these solid spheres that you couldn't cut, but now we understand the atom to be composed of smaller particles, the subatomic particles I just named, the proton, the electron, and the neutron. So I want to talk about the atom. Now, before I go into the atom, before I talk about it, in science we use models. So what's a model? A model is just a representation of something else. We use models often in science because, number one, we might not be able to deal with the real thing. We might not, for whatever reason, it might be dangerous, it might be too small, it might be too big. So you're familiar with models. There's a model of the solar system. There's a model of, there's all kinds of models in science. Well, when we talk about the atom, there are several models, but the two main models, the two main ways to think about an atom, one way is called the Bohr model of an atom, or the planetary model. And then the second way to talk about an atom is the quantum model. And so both models have advantages and disadvantages. So when we talk about the Bohr model is easier to understand. I won't say it's easy, but it's easier to understand, to visualize, and it's just as simpler. The disadvantage is it's not as correct as the quantum model. The quantum model is more correct, but it's hard to visualize and it's much more complicated. So if I want to be really, really correct, I would use the quantum model. If you had chemistry courses in high school or college, you probably talked about the quantum model of the atom. In this class, we're going to deal with the Bohr model. Why are we dealing with the Bohr model? Well, number one, it's exactly what we need to understand the nature of voltage, current, and resistance. And number two, using the quantum model will be overkill. We don't need to go to anything that detailed. So I'm going to introduce you to the Bohr model of the atom, or the planetary model of the atom. If you were taught about atoms and atomic theory in high school or other places, you probably already looked at the Bohr model. So Bohr was a famous physicist, Niels Bohr, and he gave us this model of the atom, where the atom consists of mainly two regions. You have the region in the middle, and you have the region on the outside. I'm just going to draw these dotted lines on the outside. Now, as I go through the discussion of the Bohr model of the atom, remember, I'm trying to draw something that's three-dimensional on a two-dimensional surface. So right now, I'm drawing this dotted line represents a circle, and this is a circle, but it's really a sphere. It's like a ball. So you got to remember, this is three-dimensional. Just kind of use your imagination. So what am I drawing here? Well, the basic atom has a center part that we call the nucleus, and this dashed line doesn't really exist around it. The dashed line represents a path or trajectory. It's the path that the electron, which is another subatomic particle, I'm just going to draw a smaller sphere right here. So the center piece represents the nucleus, and then that small piece here represents an electron, We know about these subatomic particles. There's three of them. There's one called the electron, one called the proton, and the other is the neutron. And the proton and the neutron, they live right here. They live in the nucleus of the atom. They don't move. They're not free to move. Whereas the electron lives on the outside of the nucleus, and it moves around the nucleus. It spins around or revolves around the nucleus at a very, very high speed. It moves around the nucleus at the speed of light. So what I'm representing here is just a very simple atom with the centerpiece. Let's say the centerpiece is one proton and one neutron. I'm sorry, one proton and one electron. So if you recognize this, maybe you had a chemistry class or something, you might recognize the simplest atom in the universe. The simplest one is the hydrogen atom. Hydrogen. Hydrogen consists of one proton in the nucleus and one electron revolving around that nucleus. And what I'm not showing the neutrons. The neutrons also exist in the nucleus. So the nucleus might be composed of, if I have a more complicated nucleus, it might be composed of a couple protons and maybe some neutrons. But I won't show the neutrons. Why won't I show the neutrons? Well, it turns out that neutrons don't contribute to electrical properties at all. They don't contribute to any of the electrical properties of the atom. So it doesn't make sense to show them. So neutrons are not important for what we talk about in this class, but just understand they do exist and they are located in the nucleus of the atom. There's only one time we'll talk about neutrons. There's an example when we talk about, later in the course, when we talk about magnetism. I'll mention neutrons briefly and we'll talk about them. But for the rest of the time, we won't bring the subject up at all. So I tend to only show positive and negative charges. I show protons and I show electrons. Now, if you look at my terrible drawing of the atom, you'll notice that a couple things. Number one, you'll notice that I drew the proton bigger than the electron. I did that on purpose. I drew the proton bigger than the electron. And I did it on purpose because in reality, the proton is way, way more massive than the electron. The proton is about 2,000 times more massive than the electron. So I don't know if I have this drawn to scale, but imagine this thing is about 2,000 times more massive, bigger than the electron. That's important for us because what you're going to learn in this class is if I want to make electric current, what I got to do is move charge. Now, we haven't talked about charge yet. We will. We'll talk about it. But I'm just kind of jumping ahead. If I want to make electric current, which is what I want to do, if I want to make electric current, I have to move charge. And there's only two places we can get charge. We can get charge from here, the proton. We can get charge from here, the electron. And since electrons are so small in comparison to the proton, I got to move charge. So basically, I got to move either plus or minus charge. If I want to make electric current, it's much easier to move a small mass than it is a big mass. So when we define electric current, we'll define it as the flow of electrons and not protons. One reason is because electrons are so small, they're much easier to move than the massive proton, which is 2,000 times more massive than the electron. That's one reason we move electrons instead of protons. The other reason is the proton is located in the nucleus of the atom, and it's really not easy to get to separate, to move. So that's one thing I want you to think about. The other thing is, I mentioned already that the electron is not just sitting there. The electron is doing two things. The electron is moving around its own axis and is moving around the nucleus at the same time. Electrons have what we call spin. And that turns out to be really important later on in the semester when we talk about magnetism. Magnetism is related to the spin and the revolving of the electron around the nucleus. Again, that's a topic for later on in the semester, but worth bringing up here. And the final thing I want to call to your attention is that I already mentioned how fast is this electron moving. The electron is moving at the speed of light. What is the speed of light? The speed of light is 186,000. And you're used to thinking miles per hour. We drive 55, 60 miles per hour. This ain't that. This is 186,000 miles per second. That's pretty fast. Light travels at 186,000 miles per second. That's 3 times 10 to the 8 meters per second. If you write that out of scientific notation, 300 million meters per second. A meter's about the length of a yardstick. 300 million of those in 1 second. So, needless to say, light's pretty fast. So we have an electron moving around the nucleus of an atom. It's moving so fast that the electron is literally everywhere at once. The electron is moving so fast around something so small, it's literally everywhere at once. So much so that when chemists talk about electrons, in chemistry I heard the term electron cloud. I've never heard that term before. An electron cloud, literally, it's a cloud of electricity around the nucleus because it's moving so fast. You know how when you have a fan, like a window fan to keep you cool, and the fan is off, and the blades are just sitting there, and then you turn the fan on, and the blades start to spin, and they spin so fast, it looks like one solid disc. Those fan blades are moving so fast that they're really everywhere at once. It's like a solid disc. This is the same way, only remember, this is 3-dimensional, not 2-dimensional. So it's really that this electron is moving around the speed of light in this sphere of negativity, and it's really everywhere at once. Now, it's helpful to visualize that because that's going to help us understand the nature of resistance. What is resistance? And understanding that these electrons are everywhere at once, you'll have a mental picture for it. When you think about resistance, you'll know exactly what it is that we're talking about from a physics point of view. What is resistance? And then the other thing I want to talk about, I talked about the physical sizes already. I mentioned that at least the mass of the proton is 2,000 times, approximately 2,000 times more massive than the electron. But let's talk about physical sizes. And I also want to give you a reference to think about the distance. See, I got this nice distance between this proton and the electron. I got the nice, pretty distance there, and you can all see it. But drawn to scale, imagine I have a softball, like a big baseball, a softball in this hand, and I have a 10-cent piece, a dime. If I can blow the nucleus of this hydrogen atom, if I can blow it up to scale, that nucleus, if I made it the size of a softball, then the radius of the electron would be about the radius of a 10-cent piece, a dime. And it would be out here moving around the softball size mass. It'll move around. It will be located about 4 or 5 miles away. Imagine I have a softball, and then 4 miles away I have another sphere with the diameter of a 10-cent piece, 4 miles away, and that thing that's 4 miles away is moving around that softball size mass at the speed of light. If you visualize that, what you really understand is an atom is mostly empty space. I don't have it drawn here the correct way. There's no way I can draw what I just described. You can visualize it in your mind's eye, but an atom is just mainly empty space. So there's a whole lot of interesting things we can talk about when we talk about atomic theory, a whole lot to consider, but we want to kind of narrow it down to topics that's going to help us understand the nature of voltage, the nature of current, and the nature of resistance. Well, let me give you a few more terms that have to do with atoms, and then I want to move on to some ideas that's going to help us understand voltage, current, and resistance. This is I mentioned this was a representation of the simplest atom in the universe, and that's hydrogen. I'm showing one electron and one proton. Well, the next atom up on the list, I guess, and that next simplest atom would be helium. And the difference between helium and hydrogen, the difference is in something called the atomic number. Let me talk about atomic number. The atomic number of an atom is equal to Now, a lot of students get this wrong. They say it's equal to the number of electrons. But the atomic number is actually equal to the number of protons that live in the nucleus of the atom. The atomic number is the number of protons that live or that are in the nucleus of the atom. So for instance, I mentioned hydrogen. Hydrogen has 1 proton in the nucleus, so hydrogen has an atomic number of 1. Helium has 2 positive charges, 2 protons in the nucleus, so helium has an atomic number of 2. It turns out that it's very useful to classify all known elements. An element is just a group of atoms. It's useful to classify these atoms or elements by atomic number. And so there's a list, and you guys are probably already familiar with it. Definitely if you had chemistry or physics, you know about it. It's called the periodic table of elements, the periodic table. And I did put one of those periodic tables up on Blackboard, so hopefully you got a chance to download those documents and look at it. But just in case you didn't, let's talk about briefly the periodic table. Now, you want to make sure that you have a copy of this periodic table printed out that you can use in your 3-ring binder, because you will need this periodic table for exams. Well, not for all exams, but for either exam 1 or 2, I can't remember. There may be a question where you have to use the periodic table to answer it. So what I would recommend, I know some of you are not printing the documents out. Some of you are just looking at these online, but this is one document that you want to print out. When you take the exam, you're not to have anything other than the calculator and the pencil. However, you can have your periodic table. So make sure you print it out, put it in your binder, and if we have an exam question where you need it, you'll be able to bring that in and use it. Without the periodic table, unless I give you the information in the exam itself, then you'll be kind of messed up. So please, if you're not printing the documents out, at least print out the periodic table. So let's look at the periodic table real quick. And what I want to show you is this table is organized in columns and rows. And so this first row right here, I'm looking in the upper left, is the element that I'm talking about, hydrogen. And hydrogen is atomic number 1. Is atomic number 1 for the reason I said earlier. Hydrogen has 1 proton in the nucleus. If I go across over to the right, I see I have helium. Now notice I have these symbols too, the chemical symbols, capital H for hydrogen, capital H, little e for helium, and so forth. So helium has an atomic number 2. Now, as I mentioned, some students get this wrong. The atomic number tells you not the number of electrons. This is important. The atomic number does not tell you the number of electrons. The atomic number tells you the number of protons. If you assume a neutral atom, and I'll tell you what I mean by neutral in a second. If you assume a neutral atom, then you can assume that the number of electrons is equal to the number of protons. So for example, I have helium with atomic number 2. So that tells me that helium has 2 protons in the nucleus. Doesn't say anything about the neutrons. I'm talking protons. Helium has 2 protons in the nucleus, and if I assume I have a neutral atom of helium, then that means it has 2 electrons revolving around the nucleus. So that turns out to be important when we want to classify materials. We won't do it today, but probably next class. We'll classify materials as either a conductor, semiconductor, or insulator. Those are 3 classes of materials that we use in electronics. And the way to classify a material is by looking at the electron structure of that material. So it's important to understand what I mean when I say that we assume we have a neutral atom if we assume the number of electrons and protons are equal. And I'll have more to say about that on Wednesday. All right, what else do I want to talk about here? I think that's probably it for now for this. I'll come back to this document in just a second, or maybe I'll come back to it in a little while. Now, there's a couple more terms I want to talk about. And and we're going to actually go into some detail on my next thing I want to say here. But notice that I drew a plus sign on the proton and a minus sign on the electron. Now here's where we get into things that are going to help us answer what is voltage, okay? So there's something different about the proton and electron. Well, one thing, of course, is the size. You know, we mentioned the proton is bigger than the electron. But there's this other thing called charge. Charge. And scientists do not know a lot about charge. Here's what we do know. We know there's two types of it. We know there's positive charge, and we know there's negative charge. That's what we know. We know that it's conserved. In science, certain quantities are conserved. And what I mean by conserved is you can't make it, you can't get rid of it. It just is. So one of the things you all probably recognize or remember that's conserved, we say energy is conserved. You can't make energy, you can't destroy energy. All you can do is change it from one form to another. The amount of energy in the universe is constant. You can't change it. Energy is conserved. And most people understand it's called in physics the conservation of energy principle. Most or a lot of people know about that. But there are other quantities that are conserved. Mass is conserved, right? And charge is another quantity in the universe that's conserved. So we don't make or destroy charge, but what we can do is move it around. There's a certain amount in the universe, and it is what it is. But there's two types of it. So we name one positive and one negative. So we understand that charge, even though we can't say exactly what it is, we know in the universe there's two types of it. We call one positive and we call one negative. And the other thing we know about charge is that positive charge, whatever it is, it originates or comes from the proton. Negative charge, whatever it is, it comes from the electron. So we know there's two types of charge, one plus and one minus, and we know where it comes from. We know all positive charge is going to eventually originate from protons. All negative charge comes from electrons. That we know. And there's one more thing we know. We understand how this idea of charge, we understand how things that have charge, we understand how things that have charge behave with respect to each other. Let me explain what I mean. We understand that if I have two charges and those charges are the same, I have a plus charge and a plus charge, and I try to bring them together, they repel each other, they push apart. If I have a minus charge and a minus charge, I try to bring them together, they push apart. You've done this before. You have something that you played around with before that behaves exactly the same way. You've all played with magnets. You've all played with magnets. You've taken a magnet and another magnet, and you try to push them together, they push apart. And you try to turn them around, push them together, they push apart. But I'll leave one like this and one like this, they stick together. So sometimes magnetic forces repel, sometimes magnetic forces attract. It just depends on how I have the magnet oriented. Well, it's the same way with charge. And you say it like this: if I have light charge repels, unlike charges attract. I'll say it again. Light charges repel, unlike charges attract. So if I have a plus and a plus, a proton and a proton, and I try to bring them together like this, they're going to act like those two magnets that don't like each other. They're going to push apart. Light charges repel. If I have a minus and a minus, if I try to bring two electrons in the same region, they're going to try to push apart. Again, light charges repel. But when I have a plus charge and a minus charge, what happens is there's a force, and that force is going to act to bring them together, so unlike charges attract. And that is the first law that I'm mentioning here today. That's the first law we're going to start with in this class. You want to write it down. It's called the law of charge. Write it down. Law of charge. The law of charge says like charges repel, unlike charges attract. Like charges repel, unlike charges attract. Now remember, don't lose sight of what we're trying to do. We're trying to understand the nature of voltage, current, and resistance. I want to know exactly what is a voltage. And to understand that, we're starting with this idea. This is where we start. The law of charge. Like charges repel, unlike charges attract. And so we'll come back to this idea of charge, because that word charge could be kind of tricky, as you'll see. I don't know if I'll get to it today or not, because I only have 11 minutes. But you'll see that it turns out to be a very, very important concept. Probably the most important concept on that paper. But the reason I brought up charge is I see that the nucleus has a charge that's positive, the electron has a charge that's negative, and since unlike charges attract, there's an attraction of electrons for the nucleus. There's an attraction of electrons for the nucleus. Now, I don't know if you guys, if I say perpetual motion, if you know what I mean by that. But if you know what I mean by that, and if you're, I don't know if I have any METs out there or not, but you know that it's impossible to have perpetual motion. It's impossible. Even the Earth and the moon, well, let's just deal with the Earth and the sun, the solar system. So I have the sun, it's almost like this, right? They call this Bohr model of the atom, they call it the solar system model. I have here the sun and here the Earth, and the Earth is revolving around the sun, but it's not perpetual motion. The Earth, every time it goes around, it's actually slowing down little by little. It's slowing down little by little. At a certain point, we'll all be dead and gone, but at a certain point, that revolving will actually stop. That's not perpetual motion. There's only one place where perpetual motion exists, and that's on the atomic level. There's an attraction of the electron for the nucleus, the proton. There's a pull down this way, but because the electron is moving in a straight line, if I pull something down at the same time it's moving in a straight line, then it goes around in a circle. And so this is the only case of perpetual motion that we know that exists in the universe. The movement of subatomic particles, electrons around nucleus or nuclei. And you might say, well, how is that possible? Well, a whole bunch of stuff is possible when you deal with really, really small things. The study of mechanical things in physics is called mechanics. So you study motion, speed, velocity. You study any kind of motion. In physics, they put it under the category of mechanics. But when you deal with things that move on the atomic level, then they rename it. It's called quantum mechanics. So on the quantum level, a whole bunch of things that's not possible on our level is possible on the quantum level. For instance, one example, and I don't want to get, see, my problem is I go off on these tangents in this physics stuff, and I don't get through the class, but it's interesting. In the real world, if I want something to go from here to here, it's got to translate from here and move across all these points to get to there. But in the quantum world, I can have something that exists here, disappear, and reappear somewhere else. So quantum mechanics is like mind-blowing. People who understand that, that's probably all they can do. You have to be really smart to understand that kind of stuff. So on the quantum level, which is not what we're talking about. Now, the quantum model of the atom, if we use that, deals with a lot of what I'm talking about. But again, that's like using an atomic bomb to light a cigarette. It would be overkill. We don't need that. So let me try to stay focused. Here's the point I was trying to make before I went on my tangent. If I wanted to, I can remove this electron. So if I remove the electron, right now, I want you to think about this, and I'm probably going to run out of time with this thought, but we'll pick up next class. I'm going to draw a region around this atom. This is a square. Now, if I look inside the square, how much total charge is in the square? Well, I didn't tell you about magnitudes. Let me tell you about the magnitude of charge. What we know from physics is that the proton has positive charge and the electron has negative charge. Even though the proton is much more massive and much bigger than the electron, the amount of charge each has is exactly equal. So even though the mass of this is 2,000 times the mass of the electron, this is 2,000 times more massive, the amount of charge that the proton has and the amount of charge that the electron has is exactly equal, but opposite in sign. So keep that in mind. So I want to ask, well, how much charge is in the square, in the box? And the answer would be, well, from what you just said, Singleton, the amount of charge would be 0. Because if both the electron and the proton have the same quantity of charge, but one is positive and one is negative, then no matter what number you give, it's going to add up to 0. Like if I say this is +1 and that's -1, a +1 and the -1 is 0. So the net charge in that region that I have drawn around the rectangle, the square, the net charge in that box is 0. It's 0. But here's what I could do. Suppose I remove the electron. Now follow what I'm doing. I'm going to remove the electron. I got the electron right here in my hand, but remember what I said earlier. Charge, or these subatomic particles, they're conserved. I can't just make it disappear. So all I can do is take the electron and put it somewhere else. I'm going to put that electron somewhere else in the universe. I'm going to put the electron right here. Now when I look over here, I look in that box, I look in that region, and I can ask the same question. How much charge is in the box? And you look and you say, all right, well, that's easy. I got one positive charge and no negative charge. So in the box, I have a charge of +1. So I just now charged the atom. I charged the atom. It won't be today. I'm going to run out of time. But I want to talk about what did I do to charge the atom. But I charged the atom, and a charged atom is called an ion. An ion. Let me write that down. A charged atom is called an ion. Well, let me go back. It's an ion, and I've charged the atom to be positive. Now, let me go back and put this electron back. And now the net charge in this region is 0 again. But now I'm going to go out to another atom and remove its electron. I'm going to force this atom to take that second electron. So now I have another electron here, and I ask the same question. What's the amount, how much charge is in the box, in the square region? And you're going to say, well, I got 2 negative charges. I got 1 positive charge. The net charge in the box will be a -1. So again, I have a charged atom, but this time that atom is charged to be negative. So I can have an atom neutral. That means it has the same number of protons and electrons. I have a neutral atom. I can have an atom that has a positive charge. That means I've taken some electrons away, so there's more protons in the nucleus than it is around the atom than the number of electrons. There's more pluses than minuses. So I can have a positively charged atom, or I can have an atom that's negative. If I can some kind of way force the atom to take on additional electrons, I'll have more negative charges than positive, and I have a negatively charged atom or negative ion. So I can have a neutral atom, I can have a positive atom, or I can have a negative atom, all depending on that thing called the electron. Now I got about 3 minutes, but unfortunately, that ain't enough time for me to talk about what I want to talk about next. So this is going to be a good place for me to stop. So let me pause for a second because I went through that really fast. Anybody have any questions for me on anything I talked about or anything in general? Any questions?
So you do not want us to show up tomorrow, just do the lab number 2?
Yeah, I'm going to, I don't have lab 2 posted yet, so we're not going to show up tomorrow. I got an idea what I want to do. I just got to make sure it's still available, what I want you to do for lab 2. It'll be something you can do from home. And then I'll watch the numbers. I think it was either my girlfriend or my mom. I can't remember who it was. Somebody told me the numbers were falling. It was still purple, but they were falling. So I'm going to just watch it for the next couple of days. And if it starts to drop down, then and I'm not just doing this for you. It's all my classes. I'm not holding any labs face-to-face. I'm doing everything online, which is fine. Because the first lab, I mean, it's just you're looking up something. And we got a little flexibility built into the beginning of the semester. So no, we won't meet tomorrow. But however, get up, and by tomorrow I would have posted whatever it is I'm going to have you do. The other thing is there's a universe assignment if you go to the section on homework, you'll see everything that needs to be uploaded. The universal assignment is there. You can look at that. You can do that tomorrow if you want. You don't have to do it tomorrow, but just do it. You got to watch this video. I think it's only like maybe 15, 20 minutes long. And then there's, in the week 2 folder, there's another assignment called a supplementary quiz. So you got 2 things that's going to count as a quiz grade for you to help your grade out. You got the universal assignment. That's easy. You watch a video, you write something up, you got 100 points. But then there's a supplementary quiz in the week 2 folder based on what I'm talking about now. So unless you've had this stuff before, you probably don't know enough to do it now. But by the end of the week, you should be able to do that supplementary quiz. And I don't know how I'm going to have you submit it. I may have you bring it in, next Tuesday, or I may have you upload it. I'll let you know. So, yeah, so no lab tomorrow, no face-to-face lab tomorrow. And I have some kind of assignment for you to do that's going to count as a lab assignment. Anybody else have any questions?
Yeah, what's homework 2? It said it was due February 2nd, but I ain't seen any questions for it.
Yeah, the reason I haven't is because I forgot that somebody told me the bookstore didn't have books. Did I send you guys a link to the book or not? Was this the class?
It had
I don't know.
on it.
So what I was going to do is make a copy out of my book, just like I did for the first homework. I was going to make a copy out of my book and post it up there for homework 2. Homework 2 is going to be stuff out of chapter 2 that has to do with what we're talking about. So even though you're right. Even though I reference homework 2, I don't have that document up there yet. I'll post it up tomorrow. You'll have the problems. Now, if you have your textbook, you can go right to the textbook. I can give you the list of problems, but I think like half the people don't have the textbook. So I'm going to make copies and I'll post homework 2 tomorrow. Anybody else?
My question on the practice problems or the homework one, it shows just answers for the odd numbers.
Yeah.
So am I doing just the odd numbers or am I doing all of them?
You're doing, there's a list of problems. Now, the way that works, most textbooks, that's the way most textbooks are. They'll show you only the odd number problems. So here's what you do. Usually, they give an odd problem and an even problem just like it. I don't remember exactly what your problems are. I'm saying in general, most textbooks will do it that way. They'll have an odd problem and then they'll have an even problem that are pretty much the same. So if you're doing the odd problem the right way, you can assume you're doing the even problem the right way. So I just gave those answers just so you can kind of see if you're doing it the right way. I don't really think the material on that first homework set is particularly hard. So you shouldn't have any problems with that at all. So just kind of use the problem answers as a guide just to see if you're doing it the right way. And then you're probably doing the even ones the correct way if you can work out the odd problems and get the right answer.
Okay.
So that's all that's for. So did I lose everybody? Anybody else? I still got 10 people on. 15. Any more questions?
One of my other questions I had was, can I use the TI-84CE calculator for this class, or do I need to go out and get?
No, is that one a scientific calculator?
No, it's a graphing calculator.
Do you have it right there?
I don't have it right on me. It's downstairs. But it has like the SIN mode.
Is it a TI?
Yeah.
Are you able to run down there and get it, or are you too busy?
Yeah, let me run down and grab it real quick.
Go get it. I want to look at something. Just go get it and hold it up to the camera for me.
What about the TI-83 Plus?
That works fine.
Okay.
The gold standard, if you can find one, is a TI-86. That's made specifically for electrical engineering. I got a story behind that too, but good luck trying to find a TI-86.
Quick question while you're going downstairs.
Say it again.
I said, if I handwrit the homework and was planning on giving you a hard copy,
Yeah.
will I get penalized for giving it to you next lab instead of
No.
using it?
Yeah, because I think you're going to hand in all that during the next lab. So I don't think I made that homework assignment uploadable. I don't think I did. I think I want you to turn the hard copy in. So, no, you'll be fine.
Okay, cool.
You'll be fine. Okay, can you hold your calculator up? I just want to.
Yeah.
You put it more. Okay. Yeah, I think yeah. That was okay. You can use that.
Okay.
You'll be fine. Yep.
Thank you.
That's perfect. Thank you. Okay, guys. Well, stay safe, please. Please stay safe, and I will see you guys, not tomorrow. No lab tomorrow. I'll see you guys on Wednesday. Thank you so much.
See you then.
Thank you.
Thank you.